this video, we would like to find the electric field at a point of a distance r from a charge sheet which has an areal charge density of sigma. So first we would like to highlight the electric field lines that this surface emanates. On the upper surface it would emanate in the y direction as such. Assuming that this sheet is positively charged, if it were negatively charged, the field lines would move in the opposite direction, but they would be perpendicular to the surface in both cases. So keep in mind that we do not have any electric field lines going off at an angle which is not 90 degrees. All of them move upwards at 90 degrees and they are perpendicular to the surface of our plane. I mean, they are perpendicular to the plane of our surface. Now first let's imagine once again a Gaussian surface. We will be using a cylinder again, radius r, length L. Let's just do that. So this is one big Gaussian surface which we imagine along this particular surface that we have, this charged surface. Now the electric field lines that pass through the surface will only pass through the upper and lower flat surfaces. They will not pass through the curved surface of the cylinder. As I explained earlier, you do not have any field lines flying off at an angle. They're all perpendicular to the surface. So here let us calculate the flux. We have the first equation which says that flux is the electric field multiplied by the surface area, and we have the second equation which says that flux is the charge enclosed by the body divided by the permittivity of free space. Now E is the value that we are looking for, so we are not going to sub that in just yet. What we're going to do is we're going to say that flux is equal to E times the surface area. So like I said, we are just considering the upper and lower surfaces. We are not considering the curved surface of the cylinder. And now the combined surface area of both surfaces is going to be 2 pi r squared. The upper surface is pi r squared and the lower surface is pi r squared, so combined they are 2 pi r squared. So flux is going to be E multiplied by 2 pi r squared. And now when we use the second equation, let me just make this a little shorter. Yes. When we use the second equation, we have flux equals charge divided by epsilon naught. In this case, if we would like to calculate the charge, that is going to be sigma multiplied by the area, because well, sigma is equal to the charge per unit area. So when you move the A up here, when you multiply both sides by A, you have charge is equal to A times sigma, as I have over here. Now this area over here, this circular area, it obviously has an area of pi r squared. So we can say that Q is equal to pi r squared multiplied by A. Oh no, sorry. Q is equal to sigma times pi r squared. So we just plug in that value of Q here. So that's sigma pi r squared divided by epsilon naught. Now when we equate both values, this is what we get. Let's say that E into 2 pi r squared. This over here is the value of the flux that we got first. Phi equals E times 2 pi r squared, and this is also flux, so both values are going to be equal. Now the pi's on both sides cancel out, and so do the r squareds. So that leaves us with E is equal to sigma by 2 epsilon naught. Now notice this equation. The only variable that we have here is sigma, which here we consider to be a constant because this entire sheet should have a constant charge distribution. So really this equation has no variables. So however high or low you go relative to this surface, the electric field will be the same. Suppose I'm at r equals 1 meter, that's going to be the same as me being at r equals a million meters. So that is the electric field due to a charged surface, a charged planar surface. Thank you.